Alrighty, everybody. Hey, we're gonna get into the test two, test three reactions. We're gonna go over everything, and then I'm gonna get into I'm gonna get into synthesis. So we're gonna go over the synthesis worksheet that I made. So let's get right into it. So right here we have our hydrogenation reaction, which where H2 and PD on C react with an alkene to create an alkane. And as you can see, it's a syn addition here. Um, and so just the hydrogens add to the same side. Yeah, there's not much more to that. Then we have the hydration reaction, also with alkenes. Because chapter 6 is reactions of alkenes here. So hydration, we have H2O and H2SO4 reacting with an alkene, creating a Markovnikov product, the addition of a hydroxyl group to the more substituted carbon. And I have also denoted here a hydride shift and a methyl shift, which shows that the hydrogen of a more substitute carbon adjacent to the alkene can shift over to allow a more substituted carbocation to form and allow the hydroxide or the hydroxyl group to bond to the more substituted carbon. In addition, we have a methyl shift where a quaternary carbon is adjacent to this alkene, and the only thing it can share is a methyl group. So it shares the methyl group over to the alkene and creates a more stable carbocation in the process, which is where the hydroxyl adds. Then we have the exact same thing just with alcohols, which is sulfation. It's Markovnikov addition of oxy groups. So in this case, an OR group. So this could be any alcohol on top and then H2SO4 in the bottom. But same exact process, it can also do a shift because it forms a carbocation. Nice simple reaction. Then we have hydroboration oxidation. This has both regio and stereoselectivity. So it will go to the less substitute carbon, so it's anti-Markovnikov. And the hydroxyl group and hydrogen add to the same side, so it's syn addition. So yeah, we have BH3THF, NaOH, H2O2, and H2O with an alkene react to create a anti-addition product of a hydroxyl group. And then we have the halogenation reaction, which is any halogen, two equivalents of it, with CH2Cl2 to create anti-addition of the halogens. I show here that the halogens can also rotate, or the carbons that the halogens are on can also rotate because they're attached to sigma bonds to create a syn or cis product. So we also show here that this reaction is anti-addition. So on rings, you can see the wedges and dashes. And also I've shown it here with a Fischer structure. But it's all the same process, just anti-addition. But you can also do this reaction using water or alcohol, and then the water or alcohol will add to the more substituted carbon of the alkene. And this does not do any shit because no carbocation is formed. Then we have epoxidation. Epoxidation uses something called MCPBA or a peroxy acid, and this preserves stereochemistry and it is regioselective. So if you have a choice of two alkenes to choose from, which we'll actually have an example later in the synthesis that goes over that, it will actually go to the more substituted alkene. Um, so if you're choosing between two alkenes, choose the more substituted one, and it also preserves stereochemistry as shown here. The CH3 group is actually on a wedge here. Let me just quickly draw that. But yeah, this is on a wedge, CH3, right that. And then reacts with this to create an epoxide, which is this three bonded oxygen to two carbons. And that's just kind of how epoxidation looks. And then we have ozonolysis, basically using ozone to lyse the double bonds, and that it reacts with all the alkenes within a molecule. So if you wanted to get ketones or aldehydes, this is a great way to do it for synthesis. So what you use is use O3, -78 degrees Celsius, and then use either CH3 2S or zinc and a carboxylic acid. or this just has to be an acid, but we're using carboxylic acid in this case. And you can see in this case, you create two of the same product, but just showing that it lyses the double bonds and then adds oxygens to each of them to create a dialdehyde. All right, so that covers our chapter 6 reactions. That should be good. All right, we're getting back into the reactions here. So now we're working with alkynes. So that's a triple bonded carbon. So, similar reactions to test or sorry, chapter 6 reactions with the alkenes, but it's a little different. So we're gonna go start into hydrogenation. So we have three forms of hydrogenation. The first one uses H2PDC to take an alkyne all the way to an alkane. This is a very helpful tool in synthesis if you just want to reduce the alkynes all the way to your straight chain alkanes. Let's say you wanted to re reduce, like cyanide or something, like you could do this to do that. Or if you wanted to just, yeah, reduce your alkynes. This is a good way to do it. But if you wanted to take your alkynes and make them into alkenes so you can react them with things like halogenation reaction or a hydrohalogenation reaction to do like an elimination or substitution, which we'll get into in a minute. This is a better way of going about it, where you use either H2 Lindlar's catalyst to do a syn addition of hydrogens, or you do the dissolving metal reduction, which uses sodium or lithium, NH3 in liquid form with negative 78 degrees temperature to do anti-addition of hydrogens. Either of these is fine. I just tend to remember Lindlar's catalyst. It's easier for me to remember personally. So that's what I like to use. And then we also have the hydrohalogenation, which is the same idea as alkenes, but if you do excess or 2 molar equivalents of your hydrohalogenation reactant, or sorry, reagent, it'll add to the more substituted carbon because remember, this is a Markovnikov reaction. So it'll add to the more substituted carbon of the alkyne and add two halogens to the more substituted carbon. But if you just did like 1 molar equivalent, then just one chlorine would add and one hydrogen would add, and you would still have an alkene there, which is still very possible. So you could do that as well. Hydration, it's very similar. Just instead of adding a hydroxyl group, we actually add a carbonyl group, which is a C double bonded to an oxygen. So we use H2O, H2SO4, and HDSO4 with an alkyne to create a Markovnikov product, which is the more substituted addition of a carbonyl group. And then we're just going to go hydration oxidation, come back to halogenation. But hydroboration oxidation follows a very similar principle, almost the exact same reagent, just R2BH instead of BH3, with an alkyne to create an anti-Markovnikov addition of a carbonyl group. And then with halogenation, we have the addition of two bromines anti-addition, just like in alkenes, but we don't remain, we keep the alkene. But if we did excess of this, then we would add bromines twice to both sides. So that covers our chapter 7 reactions. Now we're going to get into our test reactions, which covers SN2, E2, SN1, and E1. So let's get right into it. All right, so SN2 here is just substitution. It's concerted. And so this SN2 can react, or it can occur using weak bases, small strong bases, and large strong bases. Weak bases can do the substitution with all forms of haloalkanes, because remember, these reactions, the substitution reactions, elimination reactions, they all require a type of haloalkane or an alcohol. In this case, we're just going to be using haloalkanes. I don't believe we have any alcohol reactions that we're doing on the test. But for weak bases, you can do it with methyls, primaries, and secondary haloalkanes, except with tertiary, you cannot. There's just too much steric hindrance, so it does not occur. This can also, or SN2 can also occur with methyl and primary haloalkanes. If you go to secondary, tertiary haloalkanes with a small strong base, that's when you get your elimination product, and we'll get in that in a second. And then large strong base, you can only substitute using methyls. And another important thing to mention about the SN2 reaction is that if you perform it on a stereocenter, so let's say you had an R stereocenter, and you react it with an SN2 reaction, what's going to happen is you're going to get an inversion of the stereocenter, so that R is going to go into an S. and vice versa. And it's also best to use polar aprotic solvents, and we're going to get into solvents in a minute. But if you use polar protic solvents, that reaction is a bit slower because there's some kind of interference with the protons of the polar protic solvents with the types of bases. You're just going to have some interference. It's not going to work as well. So we like to use polar aprotic solvents. So the different types of solvents we have here, honestly, the best way to remember it is like your small strong bases are going to be like your deprotonated versions of your solvents. So in this case, OH, OR, and NH2 are deprotonated versions of our solvents, which is like water, so H2O, and then like CH3OH, so that's like HOR. And then for another one, like NH3 is our like final like solvent. So just the deprotonated versions of our solvents. And then for like our large strong base, that's just like our NaOCH3 to the third, which we'll get into in a second. Um, and to kind of go over the names, like nonpolar, there's no dipole moment in the whole reaction. The polar obviously shows that there's a dipole moment within the molecule. I meant molecule for nonpolar as well, but for the polar solvents, there's a dipole moment present. But the polar aprotic, there's not a proton present on that molecule. But the polar protic, there is a proton present in that molecule, which is the solvents. The polar protic solvents is the things I just said, which are the protonated versions of our small strong bases. So water, alcohol, and NH3. And then, yeah, so easy things to remember for like polar aprotic. Like I said, this is the thing you want to use for like your weak base, small strong base, and large strong base. I would remember just like acetone or ether, or like DMSO, THF. Like any of those are like kind of easier to remember, at least for me. So that's what I would recommend. And then on here, this is all the groups I can do like SN2. And things to mention here, the NaOH, the NaOR, and the NaNH2 are small strong bases. Everything else here is a weak base. So if it's not a small strong base and it's not a large strong base, you can assume it's a weak base. So that covers our SN2 reaction. Now the SN1 reaction is a little different from the SN2 reaction because we have the formation of a carbocation. So when we have the formation of the carbocation, the nucleophile can add to either side, or the solvent can add to either side of the molecule. So you're going to get a racemic mixture. So you're going to get a pair of enantiomers as your final product. SN1 and E1 only work with tertiary haloalkanes or tertiary alcohols. But another thing to mention is that you can only use solvents for this to occur. For SN1 or E1, you need a solvent and just a solvent. And you can use a cold temperature to force a substitution reaction because eliminations like to be hot and substitutions like to be cold. And our designation for that is that hot is like above room temperature, so above 20 degrees Celsius, and cold is below 20 degrees Celsius. And that covers SN1 reaction. As you can see here, just replacement of the bromine, which is our leaving group, with the water. The water gets deprotonated to become a hydroxyl group, and then that protonated water becomes an oxonium ion that floats around the solution as your minor product. So that covers our SN1 reaction. So our E2 reaction, we can have two types of products occur. We can either have a Zaitsev product, which is where the double bond goes to the more substituted carbon adjacent to the halogen, or we can have a Hoffman product where the double bond goes to the less substituted carbon adjacent to the halogen. And you typically get a Zaitsev product when you use a small strong base, and you get a Hoffman product when you use a large strong base. So for small strong bases, elimination E2 only occurs with secondary and tertiary haloalkanes, and that's going to give you a Zaitsev product. So the the double bond is going to form with the more substituted carbon. And then for large strong base, elimination can occur with every single haloalkane with more than two carbons. So that basically just excludes methyl. Primary can do elimination, but we don't give it a Zaitsev or Hoffman distinction because it can only eliminate in one direction. So it's immediately just E2. There's no distinction other than that. And then secondary, tertiary both give Hoffman. One other thing I should mention is that for the elimination using like small strand base, typically it is Zaitsev with all leaving groups. However, if you have fluorine, it's going to give you the Hoffman product because fluorine is a poor leaving group. And because fluorine is a poor leaving group, it's going to force a Hoffman product as a major product because the fluorine is still interacting as the elimination is trying to occur. So fluorine's going to give your Hoffman product every time. So that's just another important thing to mention. All right, and then E1 is another elimination reaction, but like SN1, it only occurs with a solvent and with a tertiary halocane or tertiary alcohol. It uses a polar protic solvant. Both SN1, E1 use polar protic solvents, and you're going to get a Zaitsev product for the elimination reaction. Another thing to mention is that, like I said before, eliminations want to be hot, so it's going to be above 20 degrees Celsius. So I use 50 degrees Celsius here to get eliminations. And then another thing to mention here, if you want to get like alkynes from like a dibromination, like you just did a halogenation to get anti-addition of like bromines or chlorines or something, what you can do is use NH2 to do a substitution reaction on either methyl primaries to get a just a substitution product of like NH2, or you can do elimination with secondary or tertiary and vicinal haloalkydes to create an alkyne. And this reaction right here is super helpful for synthesis. This one here is just like a standard SN2 reaction, so nothing too crazy here. And then for Diels-Alder, this reaction is like one of my favorite reactions because it is so useful. It's very diverse in its use, and I love using it in synthesis, as you'll see in a second. But basically, you have a diene, you have a dienophile, and the diene and dienophile react to form a cyclic compound, which in this case is a cyclohexene. And then on the right here, I've drawn this locked diene here, and it's locked because this diene is in a cyclic formation, but it's in a trans alignment. So because it's trans and I can't rotate this sigma bond because that would break the cyclic molecule, this diene is locked and this cannot perform Diels-Alder. So this is a no-go. So yeah, and then orienting the Diels-Alder. So Diels-Alder, you basically want to make sure that your opposite dipole moments are next to each other for the diene and the dienophile, which is why I have drawn my reaction like this and not this. Because basically what you do is you go to your electronegative atoms, and for like our diene here, the methyl is electropositive, and then you just literally flip-flop throughout the entirety of the molecule. So partial positive, partial negative, partial positive, partial negative, partial positive, partial negative. And then a dienophile, the hydrogen is partial positive, oxygen is partial negative, and then, partial positive, partial negative. And if I try to react the diene and the dienophile like in this orientation, it's not going to work because we have a partial negative and partial negative next to each other and partial positive here and partial positive here next to each other. So that's not going to work. They're going to repel each other. But if we put it in this formation where we flip it, just do a pancake flip of the dienophile, it'll work because the partial positive of the diene and the partial negative of the dienophile are next to each other. And like I said here, opposites attract, and this reaction will be able to occur, which is why we get this product and not this product. And right here, we're looking at the endo versus exo product. So for the reaction of Diels-Alder, you're going to get the endo product first, which endo means axial, exo means equatorial. You're going to get the endo product first because in the transition state of the Diels-Alder, the dienophile is going to stabilize the diene while it's in an endo form, because in endo form, basically the electronegative group is going to be under the diene, and it's going to stabilize the diene in reaction. So that one will form first. However, the exo product is more stable, and that will form secondarily, but it is more stable because there's less steric interaction. There's 1,3,5-diaxial interactions occurring here. There's not on the exo. But the exo takes longer to form, so endo is actually our major product here. Okay, so that covers all the reactions from last test and this test. Now let's get into some synthesis. So the way I like to do synthesis is all about reverse engineering. You look at your starting product, you look at your final product, and you got to see, what bonds break, what bonds form, what things are added, and kind of the process of how to add those specific groups or specific bonds. So, for example, this is a very easy synthesis problem. You would probably see something like this on the test, where we have this benzene, which has a bromine attached to a carbon that's just off the ring. And we can see here that we have an addition of two more carbons and a hydroxyl group. So, or sorry, we have the addition of one more carbon and a hydroxyl group because there's a carbon right here. So we have one more carbon added and the hydroxyl group. So that means we're going to have to add one carbon somehow. Um, so what we can do for that is, oh shoot, this should be one more long. Yeah, this should be one more carbon long. Let me just quickly do that. That's my bad. Okay. So yeah, now it's an addition of two more carbons. So yeah, you have to add two more carbons and you have to add a hydroxyl group in an anti-Markovnikov way. How do you add a hydroxyl group in an anti-Markovnikov way? Well, we can do a hydration reaction or a hydroboration oxidation reaction. In this case, hydroboration oxidation because it's anti-Markovnikov. And we can add carbons using a substitution reactions because we have a bromine on our starting molecule. So we can substitute that out for an alkyne, reduce the alkyne into an alkene using H2 Lindlar's catalyst, and then do hydroboration oxidation to get this final molecule here. So first react it with this SN2 reaction, where we get the NaCCH and then DMSO. DMSO, polar aprotic solvent, and then this NaCCH is an addition of an alkyne. Then we do H2 Lindlar's catalyst to get this molecule here. And then we get the addition of yeah, we have an addition, sorry. Yeah, we have the addition of the hydroxyl group and anti-addition using hydroboration oxidation. And so that's kind of the way you go about it. I like to write like little notes about kind of the process about it, like give myself, because basically synthesis is like following a recipe. So synthesis problems, you got to think about it like a recipe. Like if you were given a cake and you had to dissect it, you would first like go from the outside in. So you would first say, okay, like what's the icing being used here? You take away the icing and then you're left with three layers of cake, and you see that it requires these three different layers, and then you can take apart each layer and see in between that they each have like jam or like a filling between them, and you're like, oh, okay, there's a filling that's out of between them, and then you can break apart, you can taste the cake and say, oh, the cake is made out of this, and then reverse engineer the cake. So synthesis is just like cooking. Synthesis is like making a recipe, just backwards. So for number two, what we have here, I don't know why this is here. That should not be here. For this reaction here, we have a starting alkene with a bromine attached, and we're creating a cyclic molecule that adds two carbons here, and then also an anti-addition of a carbonyl group. And also on the cyclic ring, we have an anti-addition of a, or sorry, not anti-addition, anti-Markovnikov for the carbonyl, but then we have anti-addition of a bromine and a hydroxyl group. So we can do this by using Diels-Alder. Diels-Alder will give us the cyclic molecule. The diene is our diene, and then uh, the alkene with the bromine on it is our dienophile. That's going to react to create a bromine on the right side of the alkene here after Diels-Alder. Then we can substitute there's also should be a polar aprotic solvent here. So let's use DMAC, okay? DMAC as a polar aprotic solvent, but NaCCH. and a polar aperiodic solvent to add this alkyne. And then we can do the anti-addition of our bromines here to get this Br to an OH addition. But this, remember, could also react with the alkyne, but the alkene is more reactive than the alkyne, so it's going to react with the alkene first. So that's why we have these. But we have a pair of enantiomers. We can then filter that pair of enantiomers to create or just to isolate this molecule here. And then we can do the anti-Markovnikov addition of a carbonyl group using hydrogenation oxidation to create our target molecule, which is this. Okay, so that's number two. Number three here, this is a pretty fun one. Basically, what it requires is to create a cyclic molecule and then to split that cyclic molecule, which we will do now. So as you can see now, Diels-Alder reaction to start. Diels-Alder keeps the stereochemistry of our dienophile. So the diene reacts with the dienophile and it preserves the dienophile stereochemistry. So that's why we have an up branch and a down branch. And then we have our alkene here. And then what we can do is react that alkene with our Br2 and CH2Cl2 to have anti-addition of our bromines. We can do a double elimination of our bromines to get, that's why I use two molar equivalents of NaOCH3, which is our large strong base, and a polar aperiodic solvent to double eliminate in Hoffman direction. And then we can do ozonylysis to lyse those double bonds and create our aldehydes here. So we have two products. This is the major product I'm looking for. This is a minor product. But you can use ozonylysis to get those terminal carbonyl groups, which is it's a very helpful reaction. Love using ozonylysis. All right, number four here. This is also not too bad. Basically, it requires you just to eliminate and then add because we're just doing a addition product here. And so this, this OCH3 and the back formation or on a dash and the CH3 on a wedge, they could flip-flop and they rotate because this is all sigma bonds. So this is just one way of drawing it. This is fine. But another way would just be planar. That would also be fine as well. But like I said, do an elimination using small strong base. That gives you Zaitsev product. And then you do a solvation reaction with a double bond or the alkene to create a Markovnikov addition of a methoxide or methoxy group, which we have here. And then, yeah, that's it for that one. That's a nice two-step synthesis, not too bad. For number five, this one is pretty difficult, but this is also another Diels-Alder. So we react the cyclohexene are the, I guess, the 3-bromo cyclohexene with a diene, and the diene can create the naphthalene with the bromine on the second ring. Then we can do elimination of the bromine to do a Zaitsev elimination to the more substituted carbon. We can then use a hydrohalogenation reaction using HI in this case. Could be HCl, HBr, or HI, doesn't matter. Just remember, not HF, because fluorine's a port leaving group. And then we can do another elimination of the halogen to get with the small strong base or a large strong base. It wouldn't actually matter in this case, because you're going to get a pair of enantiomers. This one would probably be more likely to form, but you can filter it to get this one here. Or sorry, this won't be more likely to form, my bad. But you can filter it, isolate this one, and then do hydrogenation oxidation. That's going to react with both of these molecules. Remember, hydrogenation oxidation is a syn addition of a hydroxyl group and a hydrogen. So the OH could add to either side, or sorry, it could add to either side of this double bond, but this side, the OH is forced to go to the left side of the double bond. And also, this should be 2 molar equivalents because we're doing this twice, and we want to just have twice as much of the hydrogenation oxidation reagents to react with the alkenes of this double bond, or this molecule here. Okay, so that covers this reaction here. That's a fun one. This one's also not too bad. This is just going to require the addition of two carbons, and then it's going to require a Markov addition of a carbonyl group, which we can do through hydration. So what we can do, we do weak base with polarity product solvent, add an alkyne, and then do the hydration of an alkyne to get Markovnikov addition of a carbonyl group. So that's an easy one as well. That's a pretty doable one. You could get with that one on the test. Um, this one here, it just plays a little bit with a rotation, but it's also not too bad. What you can do here is rotate this 180 degrees to get the double bond going down. And then what you can do is do a hydrohalogenation to get Markovnikov addition of a halogen on this double bond, and then do a substitution of the double bond with a cyanide, and that will give us our final product here. So rotate it, and then react it with the hydrohalogenation reaction, so HCl in this case, and then do substitution. There should also be a polar A product solvent here. So let's use acetone, okay? And then that will give us our final product here. Okay, number 8. Number 8 is going to require a little bit more from you. It's going to require a halogenation to get two halogens here, and then double eliminations, and then double hydrations. So which we'll see here in a second. Or I guess it'd be double hydration oxidations because these are on terminal, or um, this hydroxyl group is on a terminal carbon, so I can assume that this one probably will be as well. So, like I said, halogenation, addition of two halogens, elimination using large strong base to get a Hoffman product, using polarity product solvent, and then you do hydrogenation oxidation of those alkenes to add the OH groups to each side, which we've done here to add them to the less substituted carbon. But remember, since this is equal substituted, the OH could also add here as well. You just need to do a filter. So I'm also going to say filter. So yeah, filter for that one as well. And then for number 9, we have a starting alkane or haloalkane, and then we're doing all this crazy stuff to it to get a cyclic molecule, different branches. So this is probably going to require anti-addition of it's going to require a halogenation reaction using alcohol. And then it's going to create enantiomers because there's no stereoselectivity here, or sorry, regioselectivity for this here. And then this is probably going to just extend from a halogen that's here. And there's going to be Diels-Alder involved as well. So yeah, first thing I do is I extend our branch here and using a weak base. And then once again, you should use a polar A product solvent. Let's use ether. Why not? Use ether, reduce it to an alkene. The alkene can react with, oh, okay. So I just kept the branch using a Diels-Alder to create our cyclohexene with the branch on it, which I guess would be 1, 2, 3. It would be 4-ethyl cyclohexene. And then you just do Br2CH3OH to get this reaction. You get a pair of enantiomers, so another filter for this as well. Right, filter. Okay, so that covers number 9. Number 10 here, this is probably the most challenging one. It just like requires a lot of kind of mental steps to it. So first thing you're gonna want to recognize is that this branch here is this branch right here. And that because this branch is 1, 2, 3 carbons away, or 2 carbons away, I guess, because we got 1, 2, 3 carbons away from this cyanide group here. We know we can do a substitution of the chlorine group with the cyanide group to get that. I know that there's probably going to be either like an ozonolysis or a hydrogenation oxidation reaction of an alkyne. But I know it can't be a hydrogenation oxidation of an alkyne if I have this MCPBA here. So it's probably going to be ozonolysis, considering we have a starting ring here. So first thing that we do, remember MCPBA is regioselective, so it's going to react with this double bond right here. That's going to, remember, preserve our stereochemistry. There's a hydrogen going up and hydrogen going down here. So I've shown this ethyl going up and this hydrogen going up for this MCPBA. And then I did ozonolysis to break open the double bond here. That creates terminal aldehydes here because we have addition of carbonyl groups on each end of the alkene, of the broken alkene. And then we have a substitution of the halogen here with cyanide using a polar aprotic solvent to create our final molecule here. So that one's not too bad. But it requires a lot of thinking about, the order steps because, we couldn't do our ozonolysis first because that would react with everything and then just completely split the molecule. So it requires you to understand, or synthesis requires you to understand that the steps have to be in a certain way in order for the synthesis to work. Okay, so this is a bonus problem that I've added. I did this one in office hours, but I thought it was so good that I couldn't pass it up. So we have here a ketone on our cyclohexene, and then unlike my other reactions, this is not going to be a Diels-Alder reaction, but we are adding our carbonyls here. And how do we get carbonyls? We can either do hydration, hydroboration, oxidation, or ozonolysis. And you'll see what it is in a second. So we first do bromination, get bromines on here, anti-addition. This gives you a pair of enantiomers, but they're both going to react to create the same thing, so we don't need a filter. Then we do replacement using weak base and a polar aprotic solvent. That gives us our alkynes on where our halogens were. Then we can reduce those alkynes to alkenes using H2 Lindlar's catalyst or dissolving matter reduction. Either would work. And then we can do hydrohalogenation of our alkenes. Remember, 2 molar equivalents at least, or excess would be fine as well, to get a Markovnikov addition of chlorines or bromines or iodines. Any of those would be okay. And then we can do a elimination here in Zaitsev fashion to get in polar aprotic solvent to get the alkene here, and then we can ozonolysis it to remove the double bond here and make that double bond a carbonyl. So that's one way of going about it, and you also get these two byproducts down here. So that should cover all of the stuff from tonight. I hope you guys have enjoyed watching, and feel free to reach out to me or any of the other TAs if you have questions or come to office hours. You guys are going to do great this test. And yeah, thank you so much for watching, and I will see you all in the next video. Thank you so much. All right, let's stop it.